right? And deciding between which of those is the product has to bring in an extra kind of concept. Okay? That extra concept, as I alluded to, kind of comes from General Chemistry 152, which is where we're looking at kinetics and thermodynamics. And it's the balance between those. So to do that, we'd have to go back and evaluate our energy diagrams. When we're talking the 152 kinetics and thermodynamics, I'm not talking about math and numbers and calculations. That's what you should have gotten out of 152, was that picture. Really, everything else was irrelevant. That's the picture you needed. Deciding where each of those levels are relative to each other, that's the mathematics that you guys calculated in 152. Okay? But what you were trying to do was make that picture. And so what we're trying to determine with our organic chemistry by looking at a chemical reaction is decide, is there a kinetic favoring or a thermodynamic favoring? And that comes from interpreting our energy diagram. The kinetic favoring is talking about the distance between the reactant and our transition state. That gap is all kinetics. Okay? So I don't care anything about the energy of the products. The gap between the reactants and the products is now the thermodynamics. That says thermodynamics, just trust me. Okay? It says it to the right. Okay? So when we look at this idea, we want to now be able to go back to the chemical structures we've drawn out and attempt to approximate an energy diagram that represents how those work. Okay? I forgot where I was going with that, so let's just skip. No, we can look at that. We'll come up with this concept of reversibility. So when we look at an energy diagram, we can say reactants to product 1, reactants to product 2. Well, which of those two products would we expect to be favored? Why product 2? There's a large difference in the thermodynamics of that energy. Why do we not evaluate the speed of the reaction? What's that?
It doesn't matter as much.
Nope. Nope. As a hint, you guys are trying to go grand scheme. There's no grand scheme. It's this diagram right here. Why do I not care about kinetics?
Because it creates a higher energy.
What is the difference in the kinetic energy or the transition state energy for those? There's no difference. Why do I not care about kinetics? There isn't a difference between the two reactions. Okay? What if I'd instead run something like this? Well, now which product is favored? We probably expect product 1 because
Less energy needed to get to it.
the activation barrier is very, very small for product 1. I would expect product 1 to win, even though the thermodynamics favor product 2. Okay? What if I gave it tons and tons of energy? Lots of heat, long time. I would probably end up seeing P2. Why do I see P2 all of a sudden show up? Didn't I say at P, I get P1? What happens if I provide tons of energy? Which product gets formed? Product 1 gets formed. Always. Product 1 is going to get formed. Why?
Because it's a little bit of energy to form it.
Yes.
Activation energy.
The activation energy is very, very low. So I will form product 1. But if I've provided tons of energy, what have I provided enough energy to do? Reverse that reaction. So I will be forming product 1, but I've also got enough energy to reverse the reaction. Eventually, okay, maybe really small amounts, but I start to form some product 2. Can product 2 reverse? No. If we look at the reverse for the product 2, going back to the starting material, that transition state, or that energy difference, is now so large, I cannot reverse product 2, which then means I establish an equilibrium that slowly ends up forming product 2 and product 2 only. That's all I end up seeing. So it's a balance between those two. So I can change the conditions to favor one or the other. Which product is favored? Product 2, because lower transition energy. And it's a thermodynamic product. It's lower energy at the product. Okay? So by comparing not just the energy of our products to each other, but also the energy of our intermediates, our transition states, we can start to draw conclusions about which product we expect and what conditions might force one product over the other. Okay? And that's looking at the pictures. But when we look, or energy diagrams, but when we ran a reaction, that mechanism, did we have an energy diagram? No. Okay? So we want to be able to draw an energy diagram by looking at individual structures. And we want to use that information to decide, does the reaction, which does it favor, and considerations for reversibility. You might say, well, do we have the ability to do that outside of an energy diagram? Okay, can I predict it without an energy diagram? Okay, well, this reaction, HCl plus H2O, potentially gives me H3O plus and Cl minus. What arrow should I put in that box? Okay, nice little hand gesture, I'll accept that. It shouldn't be this one. It shouldn't be this one. Both of those are wrong. Okay. And theoretically, everybody guessed the first one and not the other two. And nobody, Amber, guessed this one. You just don't make the mistake. We won't have to worry about it. Okay? So how did you make that guess? You didn't have an energy diagram. How did you come up with that? Based on previous knowledge about what?
Strong acids.
The definitions of these things, strong acids. We could also go through and draw conclusions if we used, whoops. Actually, do I give another example? Of course not. No, I didn't. We could go through and quantify it. We could look at pKa's. I'm sorry those didn't align perfectly. Okay, that's our hardcore 152. Looking at the pKa's to establish which way our reaction goes. Okay. How are you expected to be able to predict those different energies? Because as a hint, we've already discussed it this semester.
Based on charge, size.
Charge, size, electronegativity, resonance, induction, and hybridization. You are using those to say this one is more stable. Well, if it's more stable, what does that mean? It's lower in energy. You can then do and draw out an energy diagram. Okay? So we have two reactions shown here. Let's see if I can do this right. I want to go this and this. Two pathways, red and blue. Draw two energy diagrams. Ideally, overlay them so that you can compare what's happening. Do you have any questions on how to start that? Is that a no? You're all like, I totally got this. I'm not going to show you. You gotta. So you want help? Is that what you're saying? Okay. Where should we start our energy diagram? Reactants. Okay, so let's draw a reactant energy. Because I don't know where my diagram is going to go, up or down, and there's no quantification here, I can just draw it. There it is. There's my reactant energy. Which do you know how to rank energy better on? Okay, I know that was kind of a weird statement. It's not that bad. Purple box. Whoops. Or green box. Which one do you look at and you're like, I can tell a difference in energy between those? You have to give me one. Which one? You look in the purple box, you go, I know that those have different energies. Or you look in the green one and go, I know those have different energies. Which one do you know? There is no more or less stable yet because there's two separate boxes. So you like the purple box. Does everybody agree? You look at the purple box and like, I can label that one. That's easier. So I should do the easy one, right?
For us.
Let's take a look at the product. Let's draw in the product ones. Okay. Number one, we want to figure out where should the products be, higher or lower in energy than the reactants. That's our first step. Why lower in energy? No, unfortunately we can't get through that way because we can always add energy. We can do exo and endothermic reactions, so can't quite go there. Why is it more stable?
Because we lost the pi bond and we also...
Pi bond. We lost a pi bond. Charge is irrelevant because I'm not looking at the intermediates. Okay? All I'm comparing, because the intermediates aren't drawn on here yet. All I have is the reactant on the far left and the products. So what I'm trying to decide is where those products are relative to the reactant. R.
HBr, doesn't that...
We'll ignore HBr as well. That is actually one of the things that helps polarize this reaction and allow it to go. Okay? Remember, it's OChem, we look at the organic reagents. Okay? So I heard lower in energy because we lost the pi bond. I agree. So I'm going to draw in one of my products. And because we're color coding, we'll call that green. And just for the heck of it, we'll say that's the red one. So I'm just going to call R. And we'll find out later, maybe I'm wrong. Okay? But there's two possible products from that reactant. Okay? We have the red pathway and we have the blue pathway. Okay? So we need to evaluate those two possible products back to our reactant. Well, both of them lost a pi bond, so guess what? Both of them are lower in energy than the reactant. Okay, so should I be drawing them like this? Why no? Take it a step beyond they may not be equal. To decide that, I have to go back and decide, do they have the same energy? Okay? If I draw them next to each other, what am I stating? That they are the same. So let's take a look at those two structures. Do they have the same energy? They're both not charged. Doesn't that mean they're both the same energy? Okay, what's different about them? Why are you looking at the pi bond? Because the electrons in the pi bond, okay, keep going. Who wants to finish that thought? Pi bond electrons are higher in energy than sigma bond. Okay? P orbitals are higher in energy than s orbitals. So the pi bond is the thing I need to be evaluating. Okay? Is one of those pi bonds more stable than the other? Yes. Which one? The red one, because branched kind of works, but that's the wrong term for this. It's more substituted. Okay. We have a mono-substituted pi bond in the top example, and we have a di-substituted pi bond in the bottom example. Okay. So I now have the products drawn on here. If that was all this was, then I could go through and say, well, doop, doop, which product is favored? Okay? Because my reactants, or because this is an exothermic reaction, for the most part, the energy or the activation barrier for both of those will be roughly the same. That's the Hammond postulate. Okay, it's not always true, but that's roughly the same. Don't draw that. Sorry for people drawing that. Why should we not draw that?
We haven't evaluated the intermediate.
We haven't evaluated the intermediate yet, right? Okay. So I was just saying if that's where we were, that's what we could do. Okay. But we also have to now evaluate our intermediate. You said you could do the intermediate. So draw on the intermediate. If you've got questions on what to draw or where to start, raise your hand. That B was supposed to be an intermediate, an I. supposed to have a red eye and a blue eye. Okay. Where should the eye be? Above reactant, below reactant? Above. Why above? It's charged. What does that mean necessarily about it being above or below the B and R of our products? It has to be above because it's above the reactant. So somewhere above, I'm going to have the energy of my intermediates. Okay. This is not to scale. I just don't have a lot of space here. Okay. Which intermediate do you want it to be? Red or blue? Your call. 50-50 shot, doesn't matter. Red, there it is. Okay. So we now have the red eye. What do we need? A black eye. No, blue eye. Right? Okay. Post-healing a little bit. Where should that one be? Above or below the red eye? Why below it? Why is the blue eye more stable? And yes, it is lower in energy, but that means more stable. We're looking at a secondary carbocation as opposed to a primary. The secondary is lower in energy than our primary. And again, we still have that kind of nasty running out of space stuff. All right. Now that we've got that, what can we do? Whoops. And make sure we connect the lines across the proper ones. Red to red, blue to blue. We don't want any mismatches on those. And we now have our energy diagram. How does this help us decide what happens with our products? Well, what happens with the blue pathway? If I look just at the energy of the products, red versus blue, which is favored? Red, because it's lower in energy. It's the thermodynamic product. If I look at just now the transition states, or really our intermediates officially, which intermediate should I form first? Blue, because it's lower in energy. Oops. Okay, because I don't isolate the intermediate, that then continues on to form a product. If I form the blue intermediate, which product do I make? The blue product. And that one formed first, or formed because it formed first, or quickest, also known as kinetic. So depending on our conditions, we can push a kinetic or the thermodynamic product. Okay? We will constantly be referring back to this. Those of you in the lab looking at the Diels-Alder reaction, there's a kinetic and a thermodynamic product in the Diels-Alder. There's a kinetic and a thermodynamic product in enolates, which we haven't talked about yet. Okay? Kinetic and thermodynamics is a massive theme running all the way through. We have to be constantly thinking back to that difference and that balance between them. So what conditions could I push or use to favor one over the other? What does thermo mean? Heat. So guess what I could add to make the thermo product more likely? Heat. Well, if I add heat to the thermo, how could I prevent the thermo? Don't add heat, also known as remove heat, also known as cold. Sorry, that was kind of a burp hiccup thing. Cold or ice, low temperatures. Typically, if we're running cold, you'll see negative 78 degrees Celsius. It's just kind of the standard cold temperature to run at. What else could we do? As a hint, time is part of this. If I want just the kinetic, what should I do? Do short reaction times. Fast reactions. Okay, long reactions. Okay. Other conditions that become less relevant here but will become important later is evaluating the strength of the reagents being used. Because if I use a really strong acid, okay, or a really strong base as a starting material, what is that going to do to the energy of my reactant? If I use something that's really, really reactive, it's really, really reactive because it's unstable. And if it's unstable, it is high energy. So if I use super reactive reagents, I can drastically increase the height of the reactant, which then means my reaction starts to become very, very thermodynamic. There's a large difference between the reactant and the product. The more thermodynamic the reaction becomes, the more thermodynamic it'll favor because we'll run the reverse reaction. Or, sorry, the more active our reagent, the higher in energy, the less likely we get the thermodynamic, which sounds weird. Why would it be less likely? It has to do with reversibility. Remember, you always form the kinetic first. If the reactant energy goes through the roof, and our kinetic and thermodynamic products don't change, what happens to the reverse energy for the kinetic product? The activation energy now becomes astronomical, which means if I use a really strong base, the reverse reaction can't happen. I can't get back to the reactant to be able even to make the thermodynamic. Okay? Which seems kind of counter, but that's what's happening. If we can increase that breadth so much, we end up favoring only the kinetic. Kind of make sense? Yes?
Are you talking about an organic base or just a...
It'll come in with organic bases. We'll come back to it again. In fact, I've got a video that's just on kinetic and thermodynamics, and the tail end of that video is bringing in the situation that we just talked about. It's hard of an example here because we don't have something to look at. Okay? So, nonpolar pi bond as a base. Okay? How do we know it's going to act as a base? Sorry, what was the question? Now that I deleted everything? Was there a question, guys? You're good.
Not on this. There's just the plate bonds it.
Oh, okay. Never mind. How do we know that pi bond is going to act as a base?
Because we have a strong acid.
Look at the reagent. What's the reagent? A strong acid, which then means it's going to act as a base. Okay? So use both pieces of information to help you whittle your way through. Because if we get rid of that reagent, we don't know what it's going to act as. Okay? That's now going to change. It's going to become a different question. So, really, that did not happen at all the way I wanted it to. Okay, so we got a couple examples here. Draw what you expect the products to be. Write them out. You should be able to do the first one easily. The other two might be a little bit more challenging. If you got questions, raise your hand. So answer number 1. Come on. Pen's not working. Are we good? We good? Okay, I think I heard a yes. Number 2.
Can you do number 2?
Nope. Office hours. Number 3. So what the hell is that? That's a good answer. Number 2 is following under the exact same reasons number 1 came out as an answer. Number 3, something went sideways. An important step happened and went sideways. If you want to come talk to me in office hours, we'll go through and look at that. That reaction typically is also associated with mercury being added to it. Typically doesn't run just as sulfuric acid and H2O. Okay, you almost always see mercury sulfate. Okay, but that's what ends up happening. Okay? So with that, we move on. You guys drew your answers faster than maybe I would have talked about them, but you did. Chapter 25, radical chemistry. I just want to cover our bare bones basics on this. We're looking at free radicals due to unpaired electrons. Okay? There are common things that you need to be looking for to decide if you have a radical reaction. Okay? The structures shown are all examples of radicals of particular reagents. Okay? This one can come from ROOR, sometimes also just shown as peroxide. You could also see it as a single electron like that. Okay, so Rohr typically produces that free radical. This one's O2. Oxygen is technically a diradical species. Okay, it's got some interesting properties along those lines. The bromine radical comes from Br2 being hit with light. And then the carbon radical actually has to come from an intermediate. There aren't any easy, clean, ways to do that. It's almost always an alkane cleaving a hydrogen off to form that radical. Okay? So if you see Rohr or you see Br2, those are the two big ones, you should immediately be suspicious, or Br2 and light, you should immediately be suspicious that you are looking at some kind of free radical chemistry. The two types of free radical chemistry are not listed up there, so we'll hold on a second. The stability reactivity of your radicals are best approximated by a cation. Okay? Meaning, where is a cation most stable? What position? A tertiary position. Radicals most approximate cations. Where's the best place to have a radical? Tertiary. On a tertiary position. So if you're looking at a reaction where radicals are floating around, you want them to be more substituted. Okay? They will react with the most available electrons. That one gets insanely dicey because the availability of electrons is due to concentration. And concentration is not something that's shown explicitly in our reactions. So it comes really from experience and knowing your reagents. Okay? Radicals inherently react with nonpolar species. Okay? We're looking at alkanes and alkenes being the two drivers for our radical chemistry. And then that whole rest of the chapter whittles down into just this, the reaction summary. For alkanes, you've got chlorine, elemental chlorine and light, and elemental bromine and light. When you take a look at those two reactions, what jumps out at you is the difference between chlorine and bromine in the blue box. Less what? Less products. Okay, why? The chlorine reaction is exothermic, which means what it's trying to do is neutralize the chlorine as fast as possible. It's that reactive of a species. Because it is that reactive, it reacts with anything it encounters first, which will be hydrogen, okay? But any hydrogen. It then breaks down according to concentration dependence, and that's not for this issue, or not for this course right now. Bromine is nicer because it only produced one. The one it produced was because the hydrogen I removed was at the tertiary position so that I could make a tertiary radical intermediate. That's why that one happened. So when we're looking at synthetic schemes, Br2 and light with alkanes is what we expect to see. Okay? As soon as we bring in an alkene, we now get a little bit more flexibility for what we can do. If we look to the left corner, what do we see? Alkenes reacting with NBS and light. What kind of reaction are we doing? Substitution, okay, which is a bit weird. And I saw some weird glances out there. It's a bit weird because I'm saying alkenes and I'm doing a substitution. And alkenes should be doing additions or eliminations, okay? But we are indeed doing a substitution. It's also a bit weird because when we think substitution, we inherently think that what do we have to have? A nucleophile, a leaving group, neither of which we have in that reaction. What are we substituting? Hydrogen for a bromine. Okay? Notice we get two products. Why are we getting two products? As a hint, it's not charge, it's not size, it's not electronegativity, it's resonance. That pi bond can do resonance and help shift things around so that we get different products coming out of that. Okay? The other option is I could add just straight Br2. Well, I saw Br2 before. The issue with adding just straight Br2 is what do we get? So now we're moving to the left. That's not my left. That would be my right. The upper right corner for the red box. What kind of reaction happened? In addition. Okay. Is that a radical? That may be trickier. No, that's a standard just Br2 addition. Okay? The problem with adding Br2 to our alkenes is that it has the potential of doing an addition reaction. If I don't want the addition and I want the substitution, I have to limit the presence of bromine. Guess what NBS is? Bromine in a limited concentration. So if I want the substitution around an alkene, NBS is the reagent I got to run, not Br2. Because Br2 will tend to populate an addition reaction. Okay? At best, I just get lower yields. Straight down, what happened? Addition. Why is that in the radical chapter? We just did some additions, right? What's the product? 3, 2, 1, draw. Now, fast. You get 5 seconds. You don't draw it, you lose all points for today. 5, 4, 3, 2, 1. What's the product? Should you be able to draw the product that fast? Yes, absolutely. Okay, that sucks. Deal with it. You got to be able to get there. Okay, I know it's early in the semester, not day. The acid, HBr, gives us our H+. Those react with the electrons from our pi bond. We would then form a carbocation. Does the carbocation prefer to be centered at the tertiary position or the secondary position? The tertiary position is the one that wins out. That's why the bromine then attacks that position. And we end up with the product shown. What was the product when I add that same reagent and ROOR? The bromine went to the other position. The radical reaction or the radical addition does the opposite of our standard addition. Okay? And this is the one case where I would use this term, though I clearly hate it. This is an anti-Markovnikov addition. Okay? And it comes back to the mechanism. You're running through radical intermediates. It's those radical intermediates that dictate the substitution or the addition of the hydrogen and the bromine. That's why we get this product. Okay? Not because it's anti to Markovnikov. Okay? Kind of makes sense? So when it comes to our radicals, those are the reagents that we need to know out of it. You can read through the entire chapter 25. It'll go in through gory detail on everything we just talked about in the last 10 minutes. Or you can just do that. Just do that. Okay? And here's our lead up. Addition reactions with radicals. Focus on the reagents present, not necessarily our end result. So if we start with the HBr and the ROR. Okay? We just did this, and it in theory was review. I know, further back review for some than others. That's okay. What would we expect for our product? So again, fast. Skeleton. I know my chemistry is happening at those two positions. Hydrogen needs to go to one. Bromine needs to go to the other. Three, two, one. Hydrogen. Bromine. It's going in the anti-Markovnikov fashion. The way I would do that, I see ROR and go, it does the opposite of what I want it to. There's my answer. Kind of, sort of? Next one. Okay, do we have HBr? No. Okay, so this one immediately gets tricky. In our radicals, the first thing that happens was our initiation. Our ROR becomes rho radical. Sounds like something out of Scooby-Doo. Okay. What does our rho radical do? I just want to say rho radical a bunch now. Rho radical.
That's recorded.
Yep, it is. What's the next most reactive thing? Pi bond. So, single electron from rho radical is going to react with our pi bond. The result, there's our basic skeleton. Where do I attach rho? Either goes red or blue. Why would we put it blue? What's then at the red? What hydrogen? For the people going like, I didn't see a hydrogen, I don't know what they're talking about. Exactly. Take a look at the reagents. The very first reaction said HBr. Where does it say HBr? It doesn't say HBr, so don't assume there's hydrogen. What's at the red position? The what?
The other half of roar.
Almost, not quite. Roar, and this is one of our implied things, the ROOR, minimal concentration. Hardly there at all. So we can't drop the other half in. A what? Look back at our mechanistic curved arrows, the purple ones. Roar brings in how many electrons? 1, or our rho radical. How many does our pi bond have? 2, which means there's 3 electrons. How many arrows have I shown electrons for? 2. Where's that third electron? The tertiary position, our radical is at the tertiary position. Okay. Ooh. Is that stable? So what's it going to do? React with what? It's going to react with the next most reactive thing. Cass came up with the awesome idea of the other half of roar, but I said no, concentration fails. So can't react with roar. What else is left? Another pi bond. What do I end up making? I'm going to spin this on its head, sorry. So those of you that may have a hard time seeing that, there's the purple one. There's our radical bond, there's the black one. So those aren't dashes saying away in 4. I'm saying that's the new bond that was formed. It's the bond that was made by our radical. Kind of see those pieces now? Is that stable? What happens? It's going to keep reacting. It's going to keep reacting many times. A shape with many sides is known as a... Oh, come on.
Polygon?
Polygon. Okay, guess what we're making? A polymer. This is a polymerization reaction. As soon as we eliminate the addition reagent, the pi bond will react with itself. Okay? Pi bonds are sources of electrons. Okay? By that same token, not only are they sources of electrons, what else do they have within them? We draw that resonance. Notice that arrow, Amber. Just testing. The pi bond was a source of electrons and source of positive charge. Guess what the negative is? A nucleophile. Guess what the positive is? An electrophile. So what happens if I bring multiple pi bonds near each other? There is the potential that those pi bonds can react with each other in a polymerization type reaction. To do so, they need to be stabilized in some fashion, okay? Or they need to be initiated. That's where the radical comes in the radical polymerization. Okay? If we just have a container of alkenes, for the most part, it stays a container of alkenes. It has to produce something more stable. The polymers continue to react because we have the radical forcing them to react. Right? But if it's just a solution of alkenes, how and why would it ever change to be anything other than that? Okay, yes, those are the answers. We get it. Right? What happens if we change how our pi bonds are arranged relative to each other? For instance, what might we expect here? Well, we see roar, which means radicals. What is it going to react with? Pi bond. Are all the pi bonds the same? No. So we'll pick the most reactive or the most likely pi bond, which will be which, the left or right? Ends up being the left because indirectly, when it reacts, what do we end up forming? The most stable radical. So it's going to be thermodynamically driven. Once I now have the radical, what can that radical do? React with a pi bond. What pi bond? Well, it could be just the alkene. It could be another one of 2 carbons. And we could get a multitude of different polymerizations coming out of this. Okay? Big old nasty spider network of things. Okay? Commonly known as polyethylene or PET. What happens if we get rid of roar? Well, is there anything to initiate this? No. So we might mix those and say, not going to be a problem. They aren't going to react with each other. But then some guy by the name and last name, something Diels or maybe Alder, I don't remember which, mix those two, and that's not what happened. They didn't just sit and chill. This happened. Why would that happen? Right? Because we said the alkenes shouldn't just react. Right? Why would this be allowed to happen, but a standard vial of alkenes doesn't do that? What did it make? What kind of ring?
Hexane.
A cyclohexane. Ignore the ene for the moment. What is cyclohexane? What do we know about cyclohexane?
Very stable.
They're stable. So we've created a stable macrostructure, and we've reduced the number of pi bonds. Guess what? This product is now lower in energy than the starting material, and much more organized. That would suggest this is a decent product. How did that happen? Well, some color coding might help, but before we get into that, how many carbons are on the left side?
4.
Try again. We have 6. 1, 2, 3, 4, 5, 6. How many carbons on the right? 6. Fascinating. We took all the carbons of our reactants and we've somehow smashed them together into one thing. If I take 2 things and I smash them together and get one thing, I'm doing an addition reaction. Oh, Mike, that's why we're talking about this. This is a continuation of our addition reactions. Yes, it's just the addition reaction. Okay? It looks like a bunch of other stuff has happened. Where are those pieces? Let's color code. We'll color code the single double bond all by itself in blue. Where's that single double bond showing up in our product? I mean, there's a double bond right there. Misleading. There it is. The ones in purple are the new bonds that were formed. And I have my 1, 2, 3, 4, 5, 6 carbons. Certainly doesn't look like an obvious connection. One looks like pretty much a straight line and one looks like a ring. Almost exactly how it gets tested on the ACS. We'll provide you these straight line reagents and all of a sudden some weird cyclical crap happens. Okay? Well, before you freak out, Is there anything special in the reactant that, say, maybe you overemphasized as straight?
Sigma bond?
That green bond right there happens to be a sigma bond, and sigma bonds can rotate. What happens if I had instead rotated that and drawn it this way, and maybe spun that one like that? Does it become a little bit more apparent as to what potentially happened here? Pi electrons could come out, form sigma bond. That then means the next set of pi electrons also have to move out, because there's now too many electrons around that bottom one. So those could come out. Then that means there's too many pi electrons. Those could go there. And with that simple shifting of electrons around in kind of a cyclic nature, I end up with the cyclohexene. Okay? We started with structures that we should not or would not expect to have reacted, and yet somehow, some way, they did. Okay? What typically happens in that case is that we then acknowledge the people that discovered it, Otto von Diels and Johann Alder. I literally just made that up. Don't quote me on that. I apologize, Mr. Alder. Work together to come up with that, and we have the Diels-Alder reaction. Okay, so let's take a slightly closer look at this. Every time we look at a reaction, what we want to be thinking about the bonds that are broken and the bonds that are formed. So, what do you see? You didn't respond fast enough, so we're going to go backwards. Process of going backwards. We want to come up with names for these species. We refer to one species as the diene, and the other one as the dienophile. What is the diene? Why is it called a diene? Di for two, ene for alkene. I have two alkenes. That's why we call it the diene. Okay. Yes, there are really bad jokes with that. Feel free to look them up. Dienophile. What was phile? Loving. Diene, loving. Guess what our single double bond is? The one that's reacting with our diene. Okay? Back to the first question. What changes occurred? We have bonds broken and bonds formed. I don't care which one's which. I just want to know what things were broken, what things were formed.
Pi bond was broken?
Just one pi bond was broken. Two pi bonds were potentially broken. For those of us that have pushed through it or remember those curved arrows that I showed, it's actually 3 pi bonds that are broken. Okay? Because remember, if we added those curved arrows, pi bond came out, broken. Pi bond came out, broken. Pi bond came out, broken. So all 3 pi bonds get broken. What else? What's that?
Pi bond is formed.
A pi bond is formed. We have a new pi bond. It was a good guess, Cash. You can keep guessing.
I'm just thinking.
Oh, okay.
2 sigma bonds.
We also have 2 sigma bonds. Did I expect you to know where those pi bonds and sigma bonds were? At least the ones formed? No. I also didn't expect you to know yet the 3 pi bonds being broken. Okay, that comes from a better understanding of the reaction itself. Okay? But we now have them all addressed. If we think back to at least when I taught substitution, SN1 and SN2, okay? We looked at a substitution reaction. We broke a bond, the leaving group, and we made a bond to the nucleophile. 2 things happened. And we said, well, how could those 2 things possibly happen? And we looked at all possible ways, which was only 3, and only 2 of them were valid, and that led us to SN1 and SN2 mechanisms. Well, I've got 1, 2, 3, 4, 5, 6 things happening. Well, just like with the substitution, guess what we should do? Look at all possible ways that those 6 things could happen. How many of you are like, oh, that's not a big deal? Okay. I mean, 2 things, it's what, 2 to the n minus 1, maybe? I don't know the mathematics on how many possible ways you can do things, right? Somebody's got that math memorized? Well, easily shaking his head, you know what I'm talking about. Yeah. With 6 things, it's now not quite as simple, right? It's now 2 to the 6th. That's a few more possible options out of it. Well, I would make the argument it is not actually 6 different things happening. It is actually only 2. Why only 2, and what are those 2? You want a hint? Here's your hint. What did I just draw? Resonance structures for our starting material. Okay? So are those different than our starting material? No, they're resonance. Do I have any pi bonds? There are no pi bonds shown. Did I break any pi bonds? No. So what changed? I made a sigma bond 1, sigma bond 2, and then arguably all I did was draw a resonance there. Really my product shouldn't be drawn with the pi bond. It should just have a negative there and a positive there. How many things have changed? 2 bonds. 2 sigma bonds. That is all that happened in the Diels-Alder. I made 2 sigma bonds. Well, with 2 options again, it now narrows down. I can either make those 2 bonds at the same time or stepwise. I get 2 possible mechanisms to explain what I'm observing. Okay? That's where looking at the charges can help us understand how the reaction works and get us to the when. I would argue this sets us up with 2 types of mechanisms. One I'm calling DA1, makes sigma bond 1, then makes sigma bond 2, similar to an SN1 type reaction. We made 1 bond, or we broke 1 bond, then we made 1 bond. Or we have DA2, makes sigma bond 1 and sigma bond 2 at the exact same instant. Before we get too gun happy about writing this down, only one of those is correct. Different from the substitution, where we had 2 possible results, the Diels-Alder only has 1 mechanism. Okay? If we went back and looked at our substitution, we could go through and say SN1 produced 2 products, SN2 produced 1 product. Okay? The Diels-Alder reaction is significantly more complicated than the substitution because you're doing an addition reaction. And the addition reaction becomes more complicated because you're reacting pi bonds. And where do pi bonds exist? In p orbitals. And where do p orbitals exist? Above and below. So every result that we look at, we're going to get at least 2 products because there's always an above and below. Okay? So we would have to be careful in choosing an experiment to design how we evaluate and get at that understanding. Those of you in lab, guess what? That's what we're doing this week. We're looking at an experiment that evaluates that. Those of you not in lab, we'll come back to it after they finish doing it in lab. Okay? I would recommend that everybody looks at the Diels-Alder videos that I will post online. Okay? What we'll discuss in lecture is just the answers. Okay? This is how you get the answer in Diels-Alder. This is everything about just the answer. We'll look very little at understanding where it's coming from. That is really going to be relegated to the lab and the online content. Okay? And I will post links to make sure that's as clear as possible online. Okay? There's 2 videos. There's a pre-lab video that just says this is the setup. And there's also a Diels-Alder finale video that looks at the answers and how it builds and goes from it. For those of you that had problems with chirality, guess what Diels-Alder is? The perfect storm to destroy you. Okay? Diels-Alder is all about spatial awareness and where and how pieces fit together. It's a phenomenal reaction as a review reaction because it really forces you to be able to see and look at all those things. It becomes challenging to work with model kits, but I still would recommend you play around with model kits to figure that out. Okay? With that,
The
Yay, nomenclature. Okay. For those of you that did not know me, Duke, Shannon, Lydia, Letitia, Alexis, Waleed. Nomenclature, if you could describe it as an Achilles heel for me of organic chemistry, is my Achilles heel. It is the one thing I decided to never study. Okay? Because it's just a rule. You just have to know the rule. The rule doesn't have to make sense. It's just a rule. Someone said it's supposed to be left and you wrote lowercase left, you're wrong. Okay? That's dumb. I don't like it, but you're responsible for it. Okay? So this, if you memorize everything on that and know how to apply this one slide, you should be able to answer probably 95% of the nomenclature questions you will encounter in this course. And that includes the final. Okay? Applying it is potentially a big step, but that has virtually everything. Okay? And this is now everything. So my first semester students have seen this before. You're now responsible for everything, not just bolded stuff. Everything on there you got to nail down, okay, at some point during the course. Some of them will become more relevant. Like, for instance, we're talking about alkenes and alkynes and alkanes, and even the alkyl halides. We will be talking about ethers and alcohols. You should know how to name those. We're not talking so much about the esters, aldehydes, ketones right away, which means don't worry about naming those unless somebody puts them on a slide in like 2 slides. Okay? There is one big chapter assignment for nomenclature from our final textbook that covers everything that's in this first unit. Okay? I am tempted to make that homework due, just say it's due at the end of the semester. Does anybody care? Do you want to just have it done and out of the way so you can be like, okay, I can think about other stuff, or do you want to constantly see it? If you leave it to me, I'm getting it out of the way and just ignoring it. It's like the devil. You just sweep it under the rug. Just watch out for stepping on the horns. The other big thing that comes from first semester, we have the Cahn-Ingold Prelog rules. Funny story, Cahn-Ingold Prelog, the name of that, I didn't realize was actually what these things were referring to till probably 3 years ago. Shows how well I pay attention to nomenclature. Okay? We get a couple things that come out of it. Alkenes, you have trans, which ties to E, and you have cis, which ties to Z. I always get those backwards. The two things that go through my head, on the same side, for some reason, sounds like cis to me, and I keep that tied with the Z. Okay? The trans and E, somebody just said tranny, and that, I have no idea why that ties those two, but it ties those two. It has no meaning whatsoever beyond that, but for some reason that keeps those two tied to each other. The other one is chiral, R and S. You may see plus minus, lowercase d, lowercase l, capital D, and capital L. None of those have anything to do with R and S. Entirely separate system. If you may look at it and say, but this capital D happens to be R. It also happens to be sunny. That doesn't mean that because it's sunny, we're going to be in this classroom. Okay? So complete coincidence behind that. It's unfortunate, but that's how those things are kind of tied. If you want more information on that, we can talk more about it. Okay? After that, identify your alkene or your chiral carbon, and then just assign priorities. The biggest thing to watch out for is that your priorities are assigned according to atomic mass. Okay? That does not mean, well, the atomic masses of all of the pieces connected to that chiral atom is larger here, so that's the priority. No, it's the atom immediately attached. What is its mass? Okay? I don't care about what else it's attached to. If it is all the same, then you move out one atom. If it is still all the same, then you move out one atom. And you continue to do that move out slowly until you find your difference or your priority difference. If you don't find a difference, then you were looking in the wrong spot. Point to a new carbon and start again. Okay? Alkene rules, dealing with stars instead of priority namings, but it's roughly the same thing. The assigning R and S, the lowest priority, number 4, must be aimed away from you. Okay, that's how we decide RNS. Okay, that's the connecting then 1, 2, 3. You have to be able to draw your structures correctly. If it is not oriented away from you when you go through assign RNS, you are lucky. Okay? And lucky may get you an answer, but for whatever reason, the ACS does a good job of setting up their questions on RNS to prevent luck. Okay? Or just my luck. Okay? So always make sure it's oriented away from you. So here's our nomenclature practice. This is what we'll go ahead and end with, I think, today. I think that means we got through a reasonable amount of slides. Do we want to divide it up? Or do you guys just want to take a swing at whatever tickles your fancy? Tickling your fancy, go for it. So what is our longest carbon chain? 1, 2, 3, 3, 3, 4, 5, 6. So 6, longest carbon chain, and then assign our suffix, metheth, prop, but, pent, hex. Hex is 6 based off of that left thing, and so we would add our hex. Okay. Start our numbering to the highest priority. So where's our highest priority, left side or right side? Left side, because that is our, in fact, it doesn't really matter. It's very clearly going to be that side, because our oxygen is there. Okay. The middle carbonyl is in the middle, so it can't be highest priority. If we go to our list, the carbonyl at position 1 is what functional group? An aldehyde. The carbonyl at position 4 is ketone. Look at our priority lists, right in the middle. Aldehydes are above ketones, so aldehydes take precedence. So the aldehyde is going to determine our ending. Okay? The aldehyde will get the AL ending. Okay? So the dashes are our suffix change. Okay? What's in the parentheses? That would be the name for that functional group if it was not the highest priority functional group. Okay? So if there was an acid somewhere in there, the aldehyde would get referred to as an oxo, okay? Which will be relevant for the ketone in a second. Okay? So we would say hex out, but then it says really what I'm changing is the minus E becomes AL. But I don't see an E out here. What is missing in our rules? Ane, ene, or ein for our carbon backbone. So our carbon backbone doesn't have any alkenes or alkynes, which then by definition means it would be a hexane. There's my E. The E gets a, whoa, wrong thing. The E gets erased and becomes the hexal. Is that okay, Jenna? What's my next rule? Use number to specify the location. The number typically gets dropped out front to reference it. Okay. Sometimes you'll also see it embedded in the name. Which one's correct? Technically, the one embedded in the name that looks ugly and awful is the more correct version. It's also ugly and awful, so most people don't use it. Okay. The other part of it, do we really need the 1? It's an aldehyde. The aldehyde has to be at the end. If we know we're starting at that nomenclature anyway, the 1 is redundant. So we could drop the 1. Again, with the wrong eraser. Name substituents. Okay, this gets a bit weird. We don't really have a substituent, but we do have another functional group located at position 4. Okay, that functional group would be a ketone. So I go to my ketone list, and I would change the ene to one, or the E to one. But I had a higher priority functional group in the aldehyde, so I can't touch the ene, E. I have to use the oxo terminology. Where was the oxo located? 4-oxo-hexanal. Are there spaces in there? I don't know. I don't think so. I think you can just jam that all together. Okay, kind of makes sense? Okay, if you got to leave, go ahead and leave because we're done with time. Just real quickly, and I'll record these, so if you leave, just try and do it somewhat quietly. This is our main chain for the upper left. Right, this one gets nasty because you would think it would run straight across, but not, because the aldehyde is our highest priority functional group. Okay, so the aldehyde has to be at the front. So we're looking at 1, 2, 3, 4, 5, 6, 7, 7, which is a hept. I look at the backbone and notice there's an alkene sitting in there, which will be extra irritating, which means I need the ene. I have to specify the location of it. Let me drop in that al too. There's the al. My aldehyde is by definition at location 1, but we could include it. The ene then is starting at position 4. So I have hept 4 ene 1 al. It's a mouthful and I'm not even finished. And then I have 1, 2, 3 carbons, so a propyl. I have an OH, which is an alcohol, but that's changing the ending. I can't change the ending because the aldehyde is a higher priority functional group. The alternate name for an alcohol is hydroxy. This is where hydroxide is ultimately coming from. The propyl is located at position 3. The hydroxy is located at position 7. H comes before P, so we end up with 7 hydroxy, 3 propyl, again no space, hept 4 ene 1 al. Sweetness. Those of us looking at that extra carefully might go, we're still not done. The alkene, does it have cis-trans isomerism? Yes, have to specify it in the name. So we throw it out the very front, parentheses at position 4. Do I have the E or the Z? Okay, can I clear all of that? It's kind of messy in there, I just need to erase some space around it. Not a bad idea to show your implied hydrogens. We split it in half. I've got carbon versus hydrogen. Carbon is a higher priority than hydrogen, so I'll star that. I'll look at the other half, hydrogen versus carbon. Carbon's higher priority, so I'll star that. Cut in half parallel to the pi bond axis. Stars are on opposite sides of that line. Opposite was trans, which is E. 4E. 7 hydroxy, 3 propyl, hept 4 ene 1 al. Yippee. And I'll crank through it as fast as I can for the bottom one. Oh god, that looks awful. Hex 2, 4, 6. I have the oic acid, so I have a carboxylic acid. I'll number left to right. So there's my carboxylic acid. At position 2, I have an alkene. So that's where we have to be careful there. That 2 is actually referring to the alkene, not the acid. So position 2, I go 2 to 3. There's my alkene. At position 4, I have my oxo, 1, 2, 3, 4. There's my oxo. And at position 6, I have the hydroxy, 1, 2, 3, 4, 5, 6. What is missing from this name? Cis and trans. If it's not specified, don't worry about it. Draw whichever's easier for you. I would bet almost everybody's going to find the trans easier. Okay? These were advanced ones, but this is ultimately where you need to be. Okay? If you need nomenclature review, it's nomenclature 4 in our textbook. That's kind of the be-all, end-all summary on it. That is going to be due this unit. There's also Nomenclature 3, Nomenclature 2, and Nomenclature 1, which are all first semester. Those would be in the review in the Smart Work. So if you were curious about any kind of review questions from Smart Work, from first semester, anything that says review at the front, go back and look at those. Okay? I divided those out according to units. So nomenclature, spectroscopy, structure, and reactions. Okay, from first semester. And with that, we are done.